Any problems that we need to deal with? No? Okay. We'll jump right into these highlighted ones. Now let me see. Let me check something first. Let me go down till I get to, yeah, I do. No, that's moderate. Chapter 11. I do start renumbering. Okay. So I better put chapter 10 up here. Yeah, 1. Okay. Which of the following should have the lowest boiling point? What you want to look at is the strength of the intermolecular forces. If you have any ionic compounds, they're going to have the highest boiling point. Like sodium sulfide would be very high. And then you go to dipole-dipole and hydrogen bonding. So water is going to be relatively high. Hydrogen fluoride is going to be high. Ammonia, it won't be as high as water. But then once you get past those, look for nonpolar molecules. Nitrogen. So nitrogen should have the lowest boiling point. The highest boiling point, of course, would be the ionic compound, sodium sulfide. All right. Let's see, that was D. Number 2. Nope. No mistake. Number 3. I skipped number 2. Let's see. Here we go. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? We know the water molecule has a dipole, right? It's slightly positive down here and slightly negative up here. Let's see, that'd be 2. That would give it a dipole in this direction. Overall, but when the molecules encounter one another, I guess we could bring an oxygen in here and it could share these hydrogens, but most often it's depicted as just one associated with one hydrogen. So the oxygen negative side is associated with the hydrogen positive side of the other molecule. And B seems to fit that the best. A hydrogen from one molecule and oxygen from the other molecule. Those are involved in the bonding. Let's see. Did I skip that one? Oh, no. These are diagrams for number 4. That's why that other eraser does a better job of removing that stuff, but it leaves a ghost, so I have to use both of them. All right. Which of the following statements are incorrect concerning drawing 3? So we don't even have to consider Roman numeral 1 or 2. So notice what we have here. We have molecules of hydrogen and chlorine. So hydrogen chloride, it doesn't say whether it's an aqueous solution or not. We have to assume that since there are no water molecules shown, this is a hydrogen chloride gas. And how are they oriented? They're oriented just like you would with hydrogen fluoride, where the hydrogen is close to the chlorine for each molecule. So which one of these is incorrect? So let's look at A through E. I think we have some squirrely ones in there. 2 of the above are incorrect. So this is 2 incorrect. And D, okay, so we have to look at A, B, C, and D. Electrostatic interactions exist between the molecules. Is that true? We're looking for the incorrect one. So yes, that's true. Electrostatics. The molecules find the best compromise between attraction and repulsion. That's also true. These molecules exhibit ionic bonding. Nope, that's false. molecules do not ionic bond. Only ions ionic bond. OCS exhibits this type of interaction. What we mean by that is OCS. So without going through the Lewis dot structure, all we have to do is really consider the polarity of the molecule. And we find that we're going to be polar in that direction for this bond and that direction for this bond. But now we have to consider well, actually we do need the Lewis dot structure because we have to consider shape. But okay, so let's do it. Let's do it the right way. Oxygen is 6 electrons in the valence shell. Carbon is 4. And nitrogen is 5. So that's 15 electrons. Okay. We were given the structure as OCS. So that's minus 4 electrons. So we have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got a little imbalance in there. The carbon needs a, if I did that right, seems like it ought to be balanced. Did I count them up right? 6 for oxygen, yeah. 5 for nitrogen, 4. So that's 15, okay. 2, 4, that's 11. So 2, 4, 6, 8, 10. Okay, that's right. We have an imbalance in the number of valence electrons. So if we take these two and make a double bond there, and take these two and make a double bond there, then we have around this central atom, VSEPR says we have a linear molecule. So now we go back to which one is more polar? Well, oxygen is further from carbon. Wait a minute, sulfur. Yeah, oxygen is more electronegative than sulfur because sulfur is below. Okay, so this one should be stronger, and overall we should have a dipole that way. So we would get a similar interaction with this molecule as we did with the one represented there. Right, so that's correct. C is the only one that's the one we're looking for, the incorrect one. Number 6. Go juice on that. I think it'd work better. Usually when I have time to wipe the board down, it's already got some juice on it. We'll add some. Okay. There we go. All right. Number 6. Which best explains the following trend? We're going from, it looks like we're looking at the noble gases, helium, neon, argon, krypton, xenon. And we notice that as we move down that list, the boiling point increases. Boiling point the temperature increases, which means what? Stronger intermolecular forces. So why would that be? Because these are individual atoms, right? They can't be polar. Right? There's no bond to polarize. So what we're seeing here is London dispersion forces. And the larger the molecule, the larger the atom, the stronger the London dispersion forces, because you have more space in which to spread out your electrons. All right. So what we're looking at is London dispersion forces, pure and simple. Okay. All right. Number 7. Which of the following compounds has the lowest viscosity? Low viscosity means what? Low viscosity is proportional to what in terms of intermolecular forces? Low viscosity means runny, right? High viscosity means thick. So low viscosity would be proportional to the inverse of the intermolecular forces, right? It's runs opposite. So the stronger, excuse me, low viscosity, high viscosity, no, it's proportional to forces. Increased force, increased viscosity. High viscosity is high force. Okay, so which of the following compounds has the lowest viscosity? Which is one that flows the easiest? We would look for the one with the least, the smallest intermolecular force. And there we're at nitrogen again. People don't normally think of gases having viscosity, but they do. It's very small. I'll give you that. It's a lot smaller than, say, grease, right? Axle grease. But every compound has a measurable viscosity. And the lowest one in that group is nitrogen, because it has the weakest forces holding it together. And we can see that in its boiling point also, minus 195 degrees Celsius. Okay. Number 8. When a nonpolar liquid displays a convex meniscus. Okay, what does that look like? Draw a picture. So we have this thing in here, and we got some, this thing is too wide to easily detect the meniscus, so we'll just draw it straight across. But in a narrow tube, right, we should see a meniscus in here somewhere. And if it's convex, what direction is that? It's a hump, right? Like that. That's convex. Which of the following explains this behavior? It has a low surface tension, therefore clings to glass. We didn't. No, we never said that. Cohesive forces, we drew a balance between cohesive and adhesive forces. Right? So you've got cohesive forces working inside like that, and then you got adhesive forces pulling it to the glass. Right? It didn't say glass though, but we're assuming it's glass. So which one is stronger? If it's this way, the cohesive forces must be stronger than the adhesive forces. Right? So that's B. Now, if it were the other way around, you would have adhesive forces would be stronger than cohesive forces. And if you take that same liquid and put a small capillary in that liquid, it's not going to rise. In fact, it'll probably be depressed in that tube. But if you put a one where the cohesive forces are smaller than the adhesive forces, then the capillary action is going to make the liquid rise. So if you see a tube with a convex meniscus and it's above the level of the liquid, then there's something pulling it up. And it's not the intermolecular forces doing it. Right? It's more likely a barometer where you see the mercury is like this and it's pushed up here because there's a vacuum over it. And it's being pushed up by air pressure. Okay, 9. Which substance can be described as cations bonded together by mobile electrons? All right, that's another way of giving you the the earlier theory for metal bonding, right? The electron C model. It's where the metals are portrayed as cations in a sea of electrons, right? So the one that fits that best is one of those that's a metal, and we're looking at silver as our metal. Okay. That's it's a trick wording. 10, which of the following statements about steel is false? So how many do we have? 5. A, B, C, D, E. It contains carbon atoms in the holes of its ion crystals. Yep. It's an interstitial alloy. The presence of carbon iron bonds in the alloy makes steel harder and stronger than pure iron. That's definitely true. Pure iron is relatively soft and ductile because it lacks directional bonding. That's also true. The amount of carbon directly affects the properties of steel. Yep. So all of them are true. There are no incorrect statements in that group. Number 11. Now, if you understand why that answer is correct for each one of those, then I could easily change one up, and then you'd be able to pick it out, right? Not that I'm going to do that, but could happen. Which of the following statements is true about a p-type silicon? P-type. In order to be a p-type, silicon in its structure, in the structure of pure silicon matrix, that silicon must be replaced by something with fewer electrons, because P stands for positive. So fewer electrons means we move to the left of silicon. Boron, aluminum, gallium, indium, those would be good. It's produced by doping silicon with phosphorus and arsenic. That's the wrong direction. That's an N-type silicon. Protons are the mobile charge carriers. No. We depict them as holes, missing electrons. But it's actually still the electrons that are moving. Only the electrons move. It does not conduct electricity as well as pure silicon. Actually, it conducts better than silicon. So none of them are true. Those statements are all false. Let's see. Where am I going? I'm skipping 12, 13, going to 14. Okay. A solid crystal sodium chloride is, let's see, we have several to choose from in each answer. Let's eliminate the ones that make no sense. Let's start at the beginning. Soft or hard? Sodium chloride is hard. So it's either B or D. High melting point? Yep, that's true for both of them, because that's an ionic solid. A good electrical conductor or a poor electrical conductor? What do you need to conduct electricity? You need mobile ions or mobile electrons. For a metal, it's mobile electrons. For an ionic compound, it's mobile ions. And the only way you can get them is one of two ways. You either melt it or you dissolve it in liquid of some kind. Get those ions separated from one another, then they can carry a charge across from one electrode to the next. So D is the only correct answer out of that group. Number 15. Which of the following has the highest melting temperature? Well, definitely looking for an ionic compound if there's one there, and it looks like there is, magnesium fluoride. That should be the highest melting point, melting temperature for that group. 16, which of the statements is false? Let's see, A through E. A says diamond is a covalent crystal. Yeah, all the carbon atoms in diamond are covalently bonded to one another. In fact, if you have no flaws in the crystal, you have a single molecule in that diamond. B, the size of the unit cell of lithium and cesium is the same. Now, they may be the same type of unit cell. We're talking about the size. What determines the size? The atomic size, right? So lithium and cesium are both alkali metals, so they're probably the same unit cell, but cesium is a bigger atom. It needs a bigger unit cell. So B is false, right? B is false. And none of the statements is false. Okay, E can't be correct. So we found our answer. C and D should be true. Molecular crystals usually have low melting points. Yes. And metallic crystals are usually good electrical conductors. Yes, because they have mobile electrons. We're going to look at molecular crystals in one of our experiments. Let's see. Might be the first one. Yep, freezing point depression. We're going to use lauric acid, which is a fatty acid, and it's going to form. That's probably a misnomer. Molecular crystal. It's not really a crystal. It's a solid, yeah, but it doesn't form what we normally consider a crystal. It doesn't have. I think of crystals as having a very sharp melting point, right? You heat them along, the temperature rises, and all of a sudden they go like that. Or you're cooling them from the liquid and they go down like this and then go that. But ours is going to be more like that. Anyway, number 17. Yeah, let's just erase the rest of them. 17. How would you expect the melting point of carbon tetrachloride to compare to that of sodium chloride? Well, if you're comparing a molecular compound to an ionic compound, I would expect the melting point of this one to be melting point, that one to be much, much higher. But are we looking for a reason? It's probably asking us for a reason. Carbon tetrachloride should be lower than sodium chloride, yes, because sodium chloride forms an extended ionic crystal lattice. An extended ionic crystal lattice. Well, the key there is ionic. Crystal lattice is okay. We can go with that, but the key there is ionic. It's an ionic compound. It's going to have the highest melting point as compared to any molecular solid. Oh, there's more to it. Where carbon tetrachloride is a covalently bonded small molecule. Yes, that's true. All right, I don't want that yet. We're in the middle of a class. It's asking me for an update. The rest of them are false. In the interest of time, we found our answer. $19. At normal atmospheric pressure and a temperature of 0 degrees, which phases of water can exist? At 1 atmosphere, and 0 degrees C. Okay. This would be the freezing point of water under standard conditions. In fact, this is standard conditions for water So what phases can be present at the same time under those conditions? You can have a solid and a liquid together. Ice and water, A. And when we say water, we typically mean the liquid. Now, there's another point in there where all three of them can exist. That information is not given here. That's at the triple point. You can have all three at the same time. But if you deviate it just the slightest amount from that pressure and temperature, then you lose one of the phases. It's very sensitive. Number 20. All right. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? Okay. If we're measuring vapor pressure in, say, a closed vessel, we got a liquid here, and we got a gas phase up here, liquid phase down here, and we got what? It's given us evaporation. Yeah, evaporation. So what exists in to balance that in equilibrium, physical equilibrium? Condensation. Right. Condensation is I guess you could say, the opposite of evaporation, which would be E. Now, what about the others? Fusion is what? Fusion goes from liquid to solid. Right? So the opposite of that would be solid to liquid, would be melting. Okay. Vaporization, that's evaporation. Right, that's the same thing. Sublimation. Sublimation is going from solid straight to gas. Think of dry ice. So going back the other direction would be what? Deposition. That's not one of our choices there. Deposition. Okay. And let's see. Boiling. Well, boiling is a type of evaporation. It occurs at any number of temperatures depending on the external pressure. Deposition. I used to be an amateur astronomer. I had a 6-inch reflector telescope, and I was interested in how they did that. How did they make those? And well, I know how they make the mirrors. It has to be a parabola for various reasons, but how do you make it reflective? Right? Glass is reflective, but it's not very efficient. So you need something on the surface deposited in a uniform depth so that it will reflect light. And you can put silver on it, you can put gold on it, depending on the wavelength you want to reflect. But if you're making one that's affordable to the general public, you use aluminum, and then you coat it with some polymer that protects the aluminum from oxidation. But the way they do it is deposition, right? You get an aluminum rod here, and you put it in a vacuum chamber, and then you got your mirror down here, and you vaporize it, right? Turn it into a gas, usually with heat, right? And in that vacuum, it doesn't take much to get the aluminum to turn into a gas, and it just fills the whole chamber, and you get a settling on this. You may even have a cooling plate underneath this one. Right? Piezoelectric cooler is probably the most efficient, and it cools the surface of your mirror, and that causes the gas to deposit as a solid on your mirror. Now, I think the James Webb telescope is sitting out there at let's see, L1. or L2. I think it's L2. Lagrange point. About 1.5 million miles away from us. But its mirrors are coated with gold because we want the telescope is designed specifically to gather infrared light, and gold is the best for that. Naturally, that thing cost a pretty penny just to build it, not to mention getting it out there. You're given the following boiling point data. Which of the liquids would you expect to have the highest vapor pressure at room temperature? So highest vapor pressure, this is the one that's inverse. Vapor pressure is inversely proportional to intermolecular forces. Okay, so the higher the intermolecular forces, the lower the vapor pressure. We're looking for the liquid with the highest vapor pressure. We want the lowest intermolecular forces. And the boiling point tells us something about those forces. The lowest boiling point would be diethyl ether, right? 34.5 degrees C. That one is going to have the highest vapor pressure at any given temperature. Well, room temperature, there's that. Which, in the common vernacular, room temperature is 68 degrees Fahrenheit or 20 degrees Celsius. But for standard temperature chemistry, room temperature is 25 Celsius, which is 77 centigrade, 77 Celsius, 77 Fahrenheit, 25 Celsius. All right, 22. Which one of the following decreases as the strength of the attractive intermolecular forces increases? We just covered that. The vapor pressure, right? Vapor pressure. In which of the following processes will energy be evolved as heat? Okay, energy is involved when you go from a gas to a liquid to a solid, or a gas to a solid. Right? When the molecules get closer together, we have to give up heat to get them there. Because the intermolecular forces need to have less kinetic energy to overcome. So we cool them down. That means they're giving up heat. So if we look at our choices, heat of vaporization is going from a liquid to a gas. That doesn't work. Boiling point, similar, going from a liquid to a gas. The extent of deviations from the ideal gas law, that didn't have anything to do with our question. I probably just threw that in there because I didn't have anything else I could think of. The sublimation temperature of a solid going from a solid to a gas is the wrong direction, right? You have to add energy to get there. Vapor pressure of a liquid. That's where the, excuse me. I was looking at the wrong problem, wasn't it? 23. Yeah. Let me start over. Which of the following processes will energy be evolved? Okay, sublimation is going from solid to gas. That's absorbing energy. Crystallization. Crystallization is going from, actually, crystallization is not necessarily a phase change. I guess it could be considered a phase change. We're going from individual ions, right, in a solution, right? So you have a solvent out here. And when they crystallize, they form that bond, they drop out as a solid. So here they're individual ions. They're coming together as a solid. They're giving up energy to do that. Right? The closer you get, the lower the energy state. So this is a lower energy state than that, which means you have to give up. So the delta H would be negative. It's exothermic. There's our answer. The rest of them are endothermic. All right, we've got a phase diagram here to deal with. '25. Choose the correct statement about the diagram below. Notice that pressure on the y-axis, temperature on the x-axis, and we have phase regions. Solids usually on the left, liquid on the right, and gas below. And we're shown where the 1 atmosphere line is. So at 1 atmosphere, at a given temperature, you can go from solid to liquid and liquid to gas. That's normally how it occurs. Or if we held the temperature constant and increased the pressure, we would go from gas. If we were out there on the right, say, well, where the T sits, if we were right at the T, you could go straight up by increasing the pressure. You could go from gas to liquid to solid. So, questions. The diagram qualitatively correct for water. That's false. Why is it false? Because the equilibrium line between solid and liquid is the wrong slope. For water, the slope solid-liquid equilibrium line is negative. It has to lean back to the left, right? That's strange, right? There are not that many substances that will show that trend. So A is false. How about B? The diagram shows that the melting point of the solid increases with increasing pressure. Yeah. The melting point increases with increasing pressure. What's the melting point? It goes from solid to liquid, right? So as we increase the pressure, the temperature for that process increases because the slope is positive. Okay, so B is correct. The triple point is not above 1 atmosphere, it's below 1 atmosphere. The diagram could represent the phase diagram of CO2. Not likely, because we would have to go from solid to gas, straight from solid to gas at 1 atmosphere, right? At normal atmospheric pressure, you would have to draw a line where you would go, at that pressure, you would go from solid to gas. So 1 atmosphere would have to be, that line would have to be moved down until it gives us solid to gas. Okay, all right. So we found our answer, plus we talked about the others a little bit. How about 26? Below is a phase diagram for compound Q. You wish to purify a sample of Q that was collected at pressure. Okay, maybe I better draw this one. Either that or I wonder if I can annotate this. Here it is, annotate. Okay, I want to be able to draw a line. Maybe if I do this, oh, here we go, line. There we go. So if we collected the sample at pressure 1 atmosphere and temperature 100 K, it would be right here. So let's change this to, let's just put a dot, say. We had it right here. There. That's where we collected the sample. By subliming it. In order to sublime the sample, you should, let's see, no, you wish to purify a sample that was collected at 1 atmosphere and 100 K by subliming it. We want to go from solid to gas, right? In other words, we would sublime the sample first, and then we would condense it. So in this, we're in the gas phase there, right? As shown, we're in the gas phase. So what we want to do is go from, no, we're in the solid phase. We've sublimed and collected something. We want to purify it, right? It's a contaminated solid at that point. So we want to sublime it. We can't stay at 1 atmosphere and go and increase the temperature because that'll turn it into a liquid, right? So we have to decrease the pressure down here somewhere so that we can go to the right, increase the temperature and sublime it like that. Okay, so which one allows that? Well, let's see, where's my line? Let's go back here to line. If we bring that down to say a 1/2 atmosphere, then we can go to the right. And that will go solid to gas. And the idea there is that the contaminants will not sublime under those conditions. The reason we don't want to go very, very low pressure is because we might be able to get those contaminants to do the same thing. We don't want that. We want to get just low enough so that we can sublime the sample, the Q compound, without subliming the contaminants. Okay, so the best answer for that one is C. And we want to collect the sample as soon as we can get it into the gas phase. We don't want to go too high because then we start boiling off the contaminants, right? So it's a tricky situation. Okay, let me go back to here. Let's see, how do I get rid of my annotations? Here we go, trash. Pair all drawings. Here we go. I've never done that before, so. Let's see, we got several others in there. How about this one? Yeah, I'll be able to get this one right away. What's unique about this phase diagram? It's the slope of the equilibrium line for solid to liquid. That says the only substance we know that'll do that is water. There may be others, but we haven't been introduced to them. So, which of the following statements is false? The solid has a higher density than the liquid. All right, so if we say this solid has a higher density than the liquid, that means, oh, we're having to infer. First of all, we have to say this is probably water, which means we know the density of the liquid is higher than the solid. That's why we say A is false. See, it's a two-step process. We have to identify what the compound is in order to make that statement. And the rest of them should be, so we found a false statement, so E can't be it, and the rest of them should be true. Okay, those were the easy ones. I think I've got it mixed up in here. I tried to subdivide them into easy, moderate, and difficult, but I think I didn't manage it too well. That was easy. This is moderate. Now we're back to resetting the numbers. I need to redo this thing so it's sequential numbers. But for now, chapter 10, moderate. Which of the following is correct order of boiling points for KNO3, CH3OH, C2H6, and neon? Well, what I like to do is when I'm given this, this is an ordering problem, I like to bracket it, right? So we're talking about boiling points. Which would have the highest boiling point? Order of boiling point, the highest would be the ionic compound. So KNO3 would be the greatest, and the least would be neon. Okay. So all we have to do is say, which one has a higher boiling point? Methanol or ethane? Well, methanol has hydrogen bonding potential, whereas ethane only has London dispersion, and its London dispersions are stronger than neon. So this would be C2H6, and this would be CH3OH, methanol. The reason we write it that way rather than CH4O is this gives you some idea of the structure. And you can tell with that OH group on there that we have hydrogen bonding available. If we just wrote it as a molecular formula, there's no way you could tell. Okay. Next, number 4. Assume 12,500 joules of energy is added to 2 moles, 36 grams of water as an ice sample at 0 degrees. The molar heat of fusion is 6.02 kilojoules per mole. The specific heat of liquid water is 4.18 joules per gram per degree C. The molar heat of vaporization is 40.6 kilojoules per mole. The resulting sample contains what? Is it still solid ice? Is it ice-water mixture? Is it only water? Or is it water vapor? Okay, what we need to do here is draw a step diagram. Okay. So this is heat added. Okay. As we add heat, excuse me, that's not right. That's temperature. This is heat added. Okay, so we're starting down here with a solid, and the solid is being heated, and it's only solid. Then when we get to the melting point, we get solid and liquid. Okay, then once all the solid's gone, we heat the liquid. All right, and then once we get to this point, now we have liquid, the boiling point, we have liquid and solid. And then once all the liquid's gone, gas. Then once all the liquid's gone, then we heat the gas further. Okay? So what we got in here, for these sections right in here where you only have one material, solid, liquid, gas, those require a knowledge of the specific heat of that substance. So the specific heat there would say that the heat is equal to the specific heat for that process times the mass or the moles, right? It could be mass or moles, depending on the units of measure for this one right here. So it's one or the other, times a change in temperature. Okay? So that can be applied to this one, and that one. This one is known as, is given as the heat of fusion, where you go from solid to liquid or liquid to solid. All right? In those cases, the Q is simply equal to the heat of fusion times the change in temperature. That's it. The reason we can do that is because, no, wait a minute. Not change the temperature, because the temperature doesn't change. It's the heat of fusion times the mass or the moles, depending on the way this is written. And we can do each one of those similarly. The heat of fusion here and the heat of vaporization there. Mass or moles. Okay? So those are the formulas we have to work with. And we know that the total is 12,500 joules. So we're starting off, we're putting in heat added 12,500 joules. Okay? So which one are we going to use for this section? Right? If it's starting off This is 2 moles. Water is an ice at 0 degrees. So this is where we're starting right here. 0 degrees. So we're going to be using heat of fusion to go here. Right? We're not going to use this one. Use this one first. That's our first one. So how much heat does it take? And the heat of fusion is given as what? 6.02 kilojoules per mole. So we're using this part right here. Right? How much heat for this this right here is Q equals 6.02 kilojoules per mole times 2 moles. Right? So that yields 12.04, right? 12.04 kilojoules. So let's say we start off with 12,500 joules. We're going to subtract the first step right here to get to this point, converting all the solid ice into liquid, would be 12,040 joules, right? Because that's kilojoules and this is joules. So what do we have left? 0, 6, 4, 460 joules. Okay. So 460 joules is going to take us up this line right here. And then we use this one. Okay. So since we know how many joules we have to play with, let's put 460 joules equals specific heat of water is 4.18. 4.18 joules per gram degree C times the mass, which is 36 grams, and the change in temperature. Okay. So if we solve that for the change in temperature, if the change in temperature 0 to 100, if the change in temperature is more than 100, that means we've used up more, we've got more energy than we need to go from here to here. But if the change in temperature is in here somewhere, 0, say 50, for instance, then we know we're right in the middle of that change. So let's see, 460, right, divided by 4.18 and divided by 36, because this is in grams, we need grams here. So that change is 3 degrees, 3.05. Delta T equals 3.06 degrees C. Right, we're right down here. So the answer to that question is we have liquid water and ice together. Excuse me, only water. Excuse me. This is ice and water. This is only water. We're into the water region. We haven't made it to the gas yet. That's where drawing pictures helps a lot. And I know in the lecture, we didn't spend a whole lot of time working that type of problem. So I think that's one of the reasons I put it in here. Give us a chance to look at that type of solution to a problem. Okay, this is, we're now difficult. Okay. Oops. And we're doing 1. Okay. A crystal was analyzed with X-rays having 2.33 angstrom wavelength. So the wavelength equals 2.33 angstrom. The angle of the first order diffraction, n equals 1, was 19.2. So n equals 1, and the angle equals 19.2 degrees. Well, I think we've been using theta, haven't we? Yeah. What would be the angle for the second order? That's the word I couldn't remember in class. Order. N is the order. So n equals 2, and theta 1 here and theta 2 here. That's the question. So what kind of problem are we working with here? Well, X-ray diffraction. What formula do you need? You need the Bragg equation, right? The Bragg equation. That should be useful information. Back to this one. Make sure it's there.
It is.
Here it is. So the Bragg equation, n times lambda equals 2 times the distance between and sine theta. Okay. There are two ways to work this problem. One is we can set up two equations and fill in the values for the equations and then solve them simultaneously for this answer right here. Or we can find out what that is right there for this situation and then work the problem again, substituting that value in here. And the wavelength's not going to change, the n will change. Then we solve for sine theta again. Most of my students like it that way, right? Because they're not comfortable with algebra too much. So if we solve the first one, then n equals 1. Lambda can be, let's see. Does lambda need to be in meters? No. If lambda is in angstroms, then D is going to be in angstroms. All right. So we can use 2.33 here. Equals 2 times D sine theta, which is 19.2 degrees. Okay, now we just need to solve for this one. So this side of the equation is 2.33 sine of 19.2. Right, so we have to go. When I first started doing this stuff, we had to look it up in a table. Our calculators wouldn't do sines and cosines and tangents, trigonometry of any kind. So let's see, 19.2, it's the sine key, and this is 0.329 times 2, which gives us 0.65, I'm going to carry it out, times D. So D equals this number divided by that number, which is 3.54 distance angstroms. Oops, angstroms. What's an angstrom? That wasn't covered in our discussion, was it? An angstrom, 1 angstrom is equal to 10 to the minus 10th meters. Okay. Nanometer is 10 to the minus 9th. So this is a 10th of a nanometer. That used to be a very common unit of measure. Okay, now we can take that equation and solve it for n equals 2 times lambda equals 2 times 3.54 angstroms times sine. Oh, wait a minute. We know that one already. 2.33 sine theta. There we go. Now, first thing we want to do is solve this equation for sine theta and then do the arc sine. All right, so the 2's cancel. We just need 2.33 divided by 3.54. which is 0.658 equals sine theta. Theta equals the arc sine of 0.658. And on your calculator, it's just the function above the sine. On mine, it says a sine. That's arc sine. So we put in that value. It's already in here. So I'm just going to hit that function key, arc sine. That means this value is 41.2 degrees. Closest one is 41.1. That's probably got a rounding error in it. This one doesn't. Okay. Number 2. Chromium metal crystallizes as a body-centered cubic lattice. A body-centered cubic lattice. We got chromium here, here, and one right in the middle. Body-centered cubic. Okay. And these are all chromium. If the atomic radius of chromium is 1.25 angstroms, so R equals 1.25 angstroms. What's the density of chromium metal in grams per cubic centimeters? So we're looking for density. I think I used a capital D in density in grams per cubic centimeter. So in order to calculate that, we need mass per unit volume, don't we? All right. So let's tackle volume first. What's the volume of this cube? Well, we need the formula for relating the radius of the atoms to the volume of the cube. And let's see, body-centered cubic, BCC, the edge of that we call A, the edge of that is 4R over square root of 3. A equals 4R over square root of 3. Okay, so we can go ahead and calculate this side here in angstroms, and then we can do our unit conversions. That's what I would do. So A equals 4 times 1.25 angstroms divided by square root of 3. Okay, so about our calculator and do 1.25 and 4 times, and then square root of 3 here. Divide that into it. And I get 2.887 angstroms equals A. So this is 2.887 angstroms. Okay. So what we want to do is convert that angstroms into centimeters, right? Because if we cube the centimeters, then we'll get the volume of the unit cell. So let's go ahead and convert this to centimeters. All right, I know this relationship here. 1 angstrom is 10 to the minus 10th meters. And then we can do meters to centimeters. This is 10 squared, 100 centimeters per meter. So that gives us A equals how many centimeters? Well, this is times 10 to the minus 8. 2.887 times 10 to the minus 8, right? Minus 10 to minus 8 centimeters. Then A cubed simply cubes that value. Let's see. There it is. Okay, now I want to cube that. So I have to say 3 and then do this. So this is 2.406 times 10 to the minus 23rd cubic centimeters. Now we got our volume. Next thing we have to do is find out what mass that represents. Right? So I would start with how many atoms are in that cubic cell, that unit cell. We have 1, 2, 3, 4, 5, 6, 7, 8 at the corners with 1/8 each. So that's 1, and then 1 in the middle is 2. So we have 2 atoms. Let's see, let's do it over here. We have 2 atoms of chromium. What unit do we know that will convert numbers of atoms to mass? Molar mass. Yeah, molar mass. So we need to get this in moles. Atoms and moles. So 1 mole is 6.022 times 10 to the 23rd atoms. Go. Now we can convert moles to grams. 1 mole for chromium is, there it is, 51, actually 52.00. Rounded off 2 places. Okay, that gives us the mass. All right, so I say 2 and divide by 6.022 exponent 23 and times 52. And that's 1.727 times 10 to the minus 22 grams. So to calculate density, we have mass 1.727 times 10 to the minus 22 grams divided by volume 2.406 times 10 to the minus 23 grams, cubic centimeters. There we go. So let's see, I still got both of those in my calculator. I just need to flip them and divide. This is 7.18 grams per cubic centimeter. Okay. That's what's known as a multi-step problem. You have to go back to, what is the question? Density. There's your focal point right there. Then you go find out what this is and what that is. This is so much better than chalkboard. See, I thought mark guess was in the yeah. I taught at a private school in Georgia for 1 year, still had chalkboards, and I wore a suit every day to school. And I come home and there'd be a line across the back. I'd lean up against this thing. have to dust it off, do something. Couldn't afford to send it to the cleaner, so we did the best we could. Okay, now we're in chapter 11. We're going to talk about solutions, I think. Chapter 11. We're doing this, yeah, easy. Okay, wet my whistle. Okay, number 1. In a 0.1 molar solution of sodium chloride in water, 0.1 molar solution of water, of a substance in water, excuse me. Doesn't say what it is yet, does it? Sodium chloride. Yeah. Sodium chloride, and this is aqueous. There we go. That's how we write that. Which of the following will be closest to 0.1? All right, so A, B, C, D, and E. Right? All of these are 0.1. A is mole fraction. Mole fraction, mass fraction. That's not even mass percent. It's mass fraction. So it'd be mass over mass. Mass percent. Let's be mass over mass times 100. Right? We know that one's not going to be 0.1 because anything we get is going to be multiplied by 100. And the molality. And this is molality. Since I wrote M for mass here, I'm going to write this one out as little m is equal to molality. Okay. So with this, what does this say? This says 0.1 moles of sodium chloride per 1 liter of solution. That's a fairly dilute solution of sodium chloride. So if we had 1 liter of that solution, what would be its mass? More than likely 1 kilogram, right? Probably 1 kilogram. So it's very close to 0.1 mole sodium chloride per 1 kilogram of water. That's molality. Right here. All right, they're all not going to be the same. Mole fraction would be the fraction of sodium chloride per moles of water. And if you've only got 0.1 mole of sodium chloride in how many moles of water do you have? If you had 1 kilogram of water, 1,000 grams, right? Then 18.2 grams per mole is about between 5 and 6, right? Approximately 5.5 moles. So 0.1 to 5.5 is not going to be 0.1. Right? We know that. And mass, right? 1,000 grams and 0.1 mole of sodium chloride would be, let's see, 23 and 35, 45. 23, 35, 45. This is 58 grams per mole. So that would be 5.85 grams per 1,000 grams. That's not going to be anywhere near. Well, mass. Yeah, 5, right. That won't be 0.1. And times 100, not even 100. That would be 58 to 1,000. It's still not 0.1. Right? So we found our answer right there. Molality and molarity are usually pretty close together. The major difference is that molarity, it responds to temperature. Molality doesn't. Molality is independent of temperature because there's no volume term in it. Right? If you're talking numbers of things and mass of things, doesn't matter what the temperature is. All right, number 2. Which of the following concentration measures will change in value as the temperature of the solution changes? Okay, mass percent, no. Mole fraction, no. Numbers to numbers. Molality, nope. Molarity, yes. Molarity will change with temperature. Fortunately, if the concentration is, let's see, Actually, it's not too dependent on concentration. It's the volume we're worried about. So if we go from 22 degrees to 23 degrees, not going to have that much impact on your concentration, unless you're working at hundreds of percent deviation. Then you're talking about a significant impact. But as a practical matter, actually making up the solution, you will notice if you're making up a liter of solution in your volumetric flask, right, here's your mark for a liter. And if I fill it up with water at, say, and it's an exothermic reaction, so the temperature jumps up to like 35 or 40, right? And I fill it up to here, right on that mark right there. Let it cool to room temperature, it'll be down here. So it does make a difference if the temperature is that great of difference. So if it's an exothermic reaction, you can fill it up to the mark and wait and refill it later. But if it's an endothermic reaction, it's going to, wait a minute, exothermic, too high, and then it cools down. Yeah, that's right. Endothermic, then it absorbs heat and it shrinks it. And if you bring it up to the mark at a cooler temperature, then when it warms room temperature, you're above the mark. And you're essentially screwed. So if it's an endothermic reaction, you want to keep that first fill down way down here. And then as it warms up, it's going to move up like that, and hopefully it won't get to your mark. And then you can finish it off. Okay, 3. Which of the following chemical or physical changes is an endothermic process? All right, endothermic, that is, it absorbs heat. If we evaporate water, how do we go from a liquid to a gas? You have to increase the kinetic energy of the molecules. And we do that by absorbing energy. That is an endothermic process, evaporation of water. Combustion of gas, definitely exothermic. You mix sulfuric acid and water, it's going to get hot. I mean, really hot. In fact, that's why we say, do as you ought to add acid to water. Add a little bit of acid to a lot of water, which absorbs all that extra energy that's being given up. Right? If you add water to concentrated sulfuric acid, it's going to get so hot that it'll boil and just spatter everywhere. Freezing of water, if we're going from a liquid to a more stable, lower energy state, solid, going to give up energy. Not absorb energy, it's exothermic. Okay, so A is the best answer for that one. Number 4. Which statement about hydrogen bonding is true? Hydrogen bonding is the intermolecular attractive forces between two hydrogen atoms. Okay, you got to expect some silly answers in here. The hydrogen bonding capabilities of water molecule causes, let's see, that's butane, to be more soluble in water than CH3OH. No, it's the other way around. Right? Butane is less soluble in water than methanol. So A and B are false. C, hydrogen bonding of solvent molecules with a solute will not affect the solubility. That's as false as it can be. The attraction of the solvent molecules to the solute is essential in our 3-part schematic for solubility. Right? Remember, you have to break the bonds of the solute, have to break the bonds of the solvent, make a hole, and then they have to come back together in the 3rd step. Right? So C is also false. Hydrogen bonding interactions for D between molecules are stronger than the covalent bonds within the molecule. Okay, and I propose that one as a what if. What if those external bonds, those intermolecular forces were stronger than the intramolecular forces? You would have no molecules. They'd all get ripped apart, right? So D cannot be true. That's an axiomatic statement. E then is our only left, that's the only one left. Hydrogen bonding arises from the dipole moment created by unequal sharing of electrons within certain covalent bonds within a molecule. Yep. As far as it goes, that's true. Number 5. Which of the following favors the solubility of an ionic solid in a liquid solvent? Well, let's see. Let's take these in order. Does it go down to E? Yeah, it goes down to E. This is none. So A says favors the solubility of an ionic solid in a liquid solvent. In a liquid solvent. Okay. So how does it get to that point? Well, one of the things you have to do is separate these ions. That takes energy. And then they have to associate themselves with the solvent. So in order to associate with the solvent, I don't know of any ionic solvents, but there are polar solvents. Polar interactions will increase the solubility. Okay. So which of the favors the solubility? A large magnitude of the solvation energy of the ions. Okay, solvation energy, what does that mean? That is the solvation energy is the energy that is released when the solvent molecule interacts with either one of these. That gives up a lot of energy. Large magnitude means that, yes, there's a strong attraction, very large magnitude, a strong attraction between these ions and the solvent. Small magnitude of the lattice energy of the solute. Small magnitude of the lattice energy of the solute. What's the lattice energy? The lattice energy is the gas of each one of its ions yields the solid like that. So these gas ions are coming together to make that, and it gives up heat. So the small magnitude of lattice energy would be very small value here, which means you can go back this way with a little bit of energy. Okay, does that make sense? Okay, it only takes a little bit of energy to go back this way, get these guys separated so that they can interact with the solid. Okay, so that one's also true. Large polarity of the solvent, definitely. That gives you a strong interaction between these ions and the solvent. So all 3 of those are true. All of them are true. All right, that was 5. See how we doing on time? 9:30. Been at it for an hour and a half. The lecture part's 2 hours, isn't it? Oh no, it's 2.5 hours. Okay, I'll go with that. Okay, we did that one already. 6. Okay, this one is a real bear. It should not be in the easy section. In fact, I'm going to use a cheat sheet just to keep myself on course. And you guys can follow along. 6, here we go. Okay. What we're trying to answer here is between these 2 salts, potassium fluoride and rubidium fluoride. So potassium and rubidium are neighbors in the alkaline metals, and each one forms a salt of the fluoride. Okay. And we're given values for lattice energy and for heat of solution for each one, I think. Yes, heat of solution for each one. Which salt forms a stronger attraction with water? So we're looking at one particular part of that interaction, the attraction of the salt to water. All right, so let's put what we know up here. Lattice energy for Kf. Let's see, let's put Kf over here and RVF over here. And if we're talking about lattice energy, we're saying that K plus F yields Kf solid. And that energy is minus 804 kilojoules per mole. So minus 804 kilojoules per mole. We'll do the same thing for this one. Rubidium gas, chlorine gas yields rubidium fluoride solid. And this is minus 768. Minus 768 kilojoules per mole. Okay, that's given information. Heat of solution. What does that mean? Heat of solution is, all right, overall, we've got this, the heat of solution can be broken down into those three steps. Right? Delta H1, delta H2, and delta H3. We take this one typically as the energy to break the bonds of the salt. This is to make a hole in the solution, and this is the energy you get back when they come together. Okay. So let's take a look at that formula, because the information that's given combines parts of that formula. This delta H here is the lattice energy. Did I spell that right? No, it's an I. Lattice energy. So we've got that value here. The delta H of solution is given there. All right, so the delta H of solution is given as an overall, which for the first one is minus 15 kilojoules per mole. And this one, delta H of solution, is minus 24. Minus 24 kilojoules per mole. Okay. So this value would go in here, this value would go in here for the two separate solution problem solutions. What we're focused on here is that this can be taken as the heat of hydration. Okay, the energy required to separate the water molecules, and then the energy we get back when it combines with each one of these. Now, this value right here is going to be the same for both of them. Right? Going to be the same for both, because it takes the same amount of energy to split the water molecules apart. This is going to be different for each of them. So this delta H of hydration, if we solve for this term, then this difference in here is going to give us information about which one has a stronger attraction for the water molecules. Right? So we don't have to separate them. We just have to compare this value with the other. All right. So how do we solve that problem? The delta H of solution minus 15 here, minus 15 kilojoules. Can I do that with kilojoules? Yeah. Kilojoules per mole equals what? Well, the lattice energy is the amount of energy that we get back when these come together. What we're doing is putting energy in to get them to go the other direction. So this is going to be a positive 804. Okay, does everybody see that? Okay. And this is our unknown, delta H 2 and 3. Whereas this one is going to be minus 24 kilojoules per mole and positive 768 kilojoules per mole. And this is going to be delta H of 2 and 3. Let's see. This is KF and this is RB. Okay. Now we just have to solve for these two. So this delta H, KF 2 plus 3 equals, that one comes over here to be a negative. So that's a negative, let's see, negative 819 kilojoules per mole is this heat of hydration. So that term then becomes a very negative value. In other words, a lot of heat is given up. The more heat that's given up when that happens, the higher the attraction for the water molecules and the salt. Okay, that's where we're headed with this one. If we solve this one, that becomes a negative over here. So that's, let's see, 12 and 8, 9, 7, minus 792 kilojoules per mole, correct? Okay, so that's delta H 2 plus 3 RB. Okay, now we can compare. Which one is the stronger attraction? This one right here. In fact, that's the most sense that's ever made to me working the problem out. All right. So now we can go to number 7. Use the following drawing of a gaseous solution in equilibrium with a solution, a gaseous solute in equilibrium with a solution of the gas in the solvent. Which of the following statements are true when the piston is pushed down? Okay, what we're talking about here is the solubility law, or
Henry's law?
I'm sorry?
Is it Henry's law?
Yes, it's Henry's law. Henry's law. So the concentration of the solute in the solution is proportional to pressure. The external pressure of the gas over the solute. And we know that if you push that piston down, right, Boyle's law says you decrease the volume, you increase the pressure. So we're increasing the pressure by pushing that piston down. That means that the concentration in the solution should go up. They're directly proportional. So not to waste time on all the different statements, C is the best one. This will cause the pressure of the gas to increase, concentration of the dissolved gas to go up. All right, number 8. Which of the following correctly states the relationship between temperature and solubility of a substance in water? All right. What's the relationship between temperature and solubility? Well, we know that, let's take gases in a liquid first. Gas into aqueous phase. We know that all gases, temperature, all gases, solubility is inversely proportional to temperature. In other words, as the temperature goes down, solubility goes up. That's always true for gases. If we try to say the same thing for solids, right? Solubility is usually proportional to temperature. Increased temperature, increased solubility, but not always. All right, so what are our choices? Well, we got several. The best one is C. Solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That's the best answer. I can think of better answers because we're not specifying solubility of a solid versus a gas. But that happens to be the best answer out of those. Here's Henry's law. 10. A solution contains 1 mole of liquid A and 3 moles of liquid B. This solution has a vapor pressure of 314 torr at 25 degrees. Okay. This is going to be, you might have to help me with this one too. The name of the law.
Trying to read it.
It's on the tip of my tongue. Raoult. There it is. Now we're talking about Raoult's law. Actually, this one, are both of these volatile? Yeah, each one has a measurable vapor pressure. Yes, so this is modified. Raoult's law. So, if we look at this in terms of mole fraction of A gets bigger this way. And mole fraction of B then would get larger this way. Okay? So at, let's see, vapor pressure, right? Pressure here. This would be pressure A, right? It would normally, as you increase the amount of A, go like that. And if you increase B, it would go from 0 mole fraction to 1, right? 0 to 1 or 0 to 1. Then it would go, its vapor pressure would go from here, say it would be a different slope, maybe like that. Okay. So at pure B, we would have this value here. And pure A, we would have this one. And the problem says liquid A has a vapor pressure of 265, and liquid B, I went the wrong direction. Right. B is higher than A. So let's just change that. That's B, and this is A. So B is going to be higher when it's pure. B is going to be 355. And pure A is 265. Yeah, that's more accurate. Now, if this were an ideal solution, any mixture in here would give us a straight line between these 2 points right here. That would be ideal. I think the question is headed toward, is this a positive or a negative deviation from Pareto's law? So this solution has a vapor pressure of 314 torr at 25. Times 2. 314 at 25 degrees. If we have 1 mole of A and 3 moles of B, so 3 moles of B, if the total is 4 moles, then we have 3 moles here of B and 1 mole of A, right? That would give us a total of 4. And if it's ideal, then the mole fraction, let's just say the mole fraction A would be, let's do B. Mole fraction of B would be 3/4 of 0.75, right? 0.75 of 355. This would be the vapor pressure of a ratio of A to B, right? Of 1 to 3. This is A, this is B. And this would be the pressure of B. So 0.75 times 355 would be be 266. Equals, actually, we're going to have to do both of them. Torr. So what would the effect then be on A? Right? It'd still be an A to B of 1 to 3, but this would be 0.25. This would be the contribution of B to the total. This would be the contribution of A to the total. So A is 25% because it's 1 to 3 or 1 out of 4. And we're starting with 265. So a quarter of 265 is 66.3 torr. So A contributes this, and Dalton's law of partial pressure says that you add those up to get the total pressure. So adding those two together is 333. But we measure this value at what? Pressure 314, right? The actual measure is 314. This is 333, but we measure 314. So it's a negative deviation. Did I lose you?
A little.
Okay. Yeah. Question?
It looks like you did it different here, but maybe you did.
Oh, yeah. I broke it out in steps.
Okay.
Yeah. The total pressure is the pressure of A plus the pressure of B. And then we had calculation for A and a calculation for B here and here, and then added them together.
Okay.
What we ended up with was wrong. That's not right.
Okay.
No, that's not right. I need to fix that.
That's why I guess I'm confused.
Yeah, no, that's wrong. Let me say, yeah, here it is. It should be 333. And negative deviation. Yeah. 314 is what we measured. 333 is what we expect. Now you get the same answer. It's just for the wrong reasons, because it's not 620 torr. You don't add those 355 and 265
The 355 has to be multiplied by 0.75, and 265 by 0.25, then add them together. Yeah.
That must have done that years ago.
Yeah.
Yeah. Number 12. Let's see. Let's try this. A cucumber is placed in a concentrated salt solution. What will most likely happen? This is just intuitive. The cells of a cucumber have a semi-permeable membrane. So only water can move in and out. So what is the driving force? Is what we call osmotic pressure. In other words, the hypertonic solution tends to draw water out, and the hypotonic solution tends to force water in, because the concentration of water in the hypotonic solution is higher on the outside, and a hypertonic solution, the water concentration is lower on the outside, so the water moves out to try to reach equilibrium. Okay, so if this is hypertonic, which way is the water going to move? Out. Right. Water will flow from the cucumber to the solution. And what will be the effect on that cell? There's a word for it: crenation. It shrivels, gets crinkly. It goes the other way. That's known as lysis. And if it's blood, it's hemolysis. That's why you want an isotonic solution if you're ever going to do an IV on a patient. That's not much problem anymore because the solutions are already pre-prepared in plastic bags, PVC bags. It used to be when you make up your own solution, it was very important that your tech staff or your nurses knew exactly what they were doing. And you can make up isotonic solutions in a whole host of different ways. Lactated ringers is common, right? Because you don't want to stress the body with excess sodium or chloride. In an emergency, and if you don't know if the patient is diabetic or not, you don't want to use a sugar-based solution. Right? So lots of times they'll use D5W, which is dextrose 5% by weight. And that'll get you to the hospital, and then you turn them over to emergency staff and you're clear. 13, osmotic pressure depends on all but which of the following? This is 13. Well, what's the formula for osmotic pressure? Right? Should be right there on the page. Osmotic pressure. Oops, wrong one. We're in chapter 11 now, aren't we? So let's see. If I put it in here, good to check. Osmotic pressure. Where's the pi? Not in there. Ooh, I don't see it, do you? No, it's missing. Should be there. Did I put it in here to work the problems? Yeah. Molarity, gas constant, temperature. The reason we can use molarity here is because we're compensating for the temperature with that term. So osmotic pressure is typically in the atmospheres, which means that this R is going to be the 0.08206 liter atmosphere per mole K. And this temperature has to be in K This is going to be in molarity or moles per liter, right? So liters cancels liters, moles cancels moles, K cancels K and leaves us with atmospheres. All right, back to the question. Depends on which of the following. Atmospheric pressure? Nope. Molarity? Yes. Temperature? Yes. Ratio of moles of solute to solution volume? Same thing as molarity. And so the osmotic pressure does depend on temperature. Right? Pressure will increase with temperature. Pressure will increase with molarity also. Okay? Right. Let me check something. No, it's not there. All right, I have to write myself a note. We'll put it next to this correction. Check. Useful info. There you go. Next. 14. This is definition. Shaving cream is an example of which colloid type? Well, it's a foam, right? It's just a plain foam. It's a gas in a liquid. A gas in a solid would be a solid foam. All right. Now we're moving to moderate, number 3. Okay, a 0.2 molar solution of solute X. 0.2 molar X in benzene. Okay. Displays an osmotic pressure given by the formula. And this, osmotic pressure of 0.1 times R times T. So what's changed? These two terms. How do you get from there to here? Well, we would need to modify our formula with what's that correction factor called? I'm having trouble today. And don't tip my tongue. Van Hoff correction factor. I, molarity, R, T. So if this term is 0.1 from that term, this molarity is that value, right? That's 0.2. So what did I have to be? Right? I has to be 1/2, right? 0.5 times 0.2. I would then have to be 0.5, which means what? It means that in solution, this X would break up into, would dimerize. It would go from individual X's to 2 X's. Right? So this would have to go to 2X, right? If it went to 2X, that would decrease its effective concentration by half, wouldn't it? Right? You take these and put 2 of them together. Now you only have half as many particles, correct? Yep. So that means the Van Hoff correction factor would be 0.5. Or, to put it another way, X exists in benzene as X2. I think in the lecture we only covered situations where they part of them recombine and give you, say, if you have a correction factor Van Hoff of 2 and just a few of them recombined, then it'd be like reduce the value to 1.8 or 1.7. Number 4. Which of these solutions, 0.1 molal sodium chloride, 0.15 molal glucose, 0.1 molar calcium chloride would have highest vapor pressure, lowest boiling point? All right, so 1 is highest vapor pressure, and 2 is lowest boiling point. So vapor pressure responds opposite to intermolecular forces, and boiling point is a positive relationship. So if we want the lowest boiling point, we want the weakest intermolecular force, and also the weakest intermolecular force for the highest vapor pressure also. So if we look at these three, the highest vapor pressure and lowest boiling point, highest vapor pressure would be, well, let's see, the strongest, let's put them in order of intermolecular forces. How about sodium chloride versus calcium chloride? Well, 0.1 molal sodium chloride has 2 ions that are small compared to calcium. Calcium is much bigger because sodium is above, calcium is a bigger ion, which weakens the attractive forces. So calcium chloride should have a weaker attractive force than sodium chloride. Okay, but weaker than all of them is glucose. Right, because it's a molecular compound. So lowest boiling point should be glucose. And also highest vapor pressure should be glucose also. That seems counterintuitive. I mean, glucose have a vapor pressure. Well, actually, it's not just their attraction for one another, their attraction for the solvent. Right? Remember what happens to the vapor pressure when we change the concentration of the solute. These are essentially non-volatile. So when we increase the concentration of these two, we get a this is forces here. Excuse me, not to confuse it with actual values that we're talking about there. So glucose has a lower attraction to the solvent than either calcium chloride or sodium chloride. So with a lower attraction to the solvent, it should impact the vapor pressure should be much higher, right? When we dissolve it in water or dissolve it in the solvent, right? Then what effect does it have on that vaporization? Well, the glucose has a lesser attraction to the solvent. If is it aqueous? Doesn't say. We have to assume it's aqueous. Otherwise, it doesn't make any sense. And the lowest boiling point, we're saying that here we're talking about vapor pressure effect by the solute concentration. Here we're talking about colligative property boiling point with the solute concentration. So we know as we increase the solute concentration, the boiling point goes up. And it depends on the force of attraction. These have much stronger attraction here, so they will keep the boiling point. The boiling point effect will be lower. Glucose will be less of an impact. So you've got the highest vapor pressure and the lowest boiling point would be attributed to glucose, both of them. How about lowest vapor pressure and lowest boiling point? Well, lowest vapor pressure would be the most strongly attracted in there. And the lowest boiling point would still be glucose. So we would look for the, let's see, the ionic. Actually, this has an I of equal 2, and this has an I equal to 3. So the concentration here is going to be higher. That will increase the boiling point much higher, simply because of the concentration of particles. So now we're not talking about so much the intermolecular forces, but we're talking about that colligative property. So we increase at 0.1 molal, 0.1 molal versus 0.1 molal. That's for the compound. 0.3 molal for the ions and 0.2 molal for the sodium chloride. And this is still 0.1 molal. That make any sense? So the answer is C. You know what? A better explanation is not to focus on the forces. It's just colligative properties. Because when we do that, now it makes more sense. 0.1 versus 0.2 versus 0.3. 0.1 molal is going to have highest vapor pressure and lowest boiling point, simply based upon the colligative properties. And highest vapor pressure and highest boiling point. No, lowest vapor pressure and lowest boiling point. Lowest boiling point will be 0.1 and lowest vapor pressure will be 0.3. So that's calcium chloride. So I danced around the barn several times to get to the answer, and should have only taken me a simple statement. Okay, now we got to difficult, and this should be the last stretch, the home stretch for this review. Okay, a solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute and 85 grams of water. Okay, so we got solute is 53.8 grams. Mass of the solute, 53.8 grams. And in 85 grams of water. So mass of the water equals 85 grams. Okay. The vapor pressure of the solution at 60 degrees is 132 torr. So vapor pressure at 60 degrees, C equals 132 torr. Okay. The vapor pressure of water at 60 degrees is 150 torr. So this is the solution. And this is water pressure, vapor pressure at 60 degrees. C is 150 torr. Is that right? 132 for the solution, 150. Okay, what's the molar mass of the solute? Okay, molar mass, or say molecular weight, is mass per mole. We got the mass right here, 53.8 grams. We just need the number of moles. All right. So which one of the colligative properties are we dealing with here? Do I have the colligatives listed? Engine temperature, vapor pressure. Vapor pressure is mole fraction times total pressure. So if we're saying that this is the solvent, the pure solvent is 150 torr. So P0 of water is 150 torr. Okay. Now what we need is the mole fraction of water. Mole fraction of water times that value will give us 132 torr. Okay. Okay, so mole fraction of water is 132 over 150. .88. So what's the mole fraction of, do they give it a letter? No, solute. Is 1 minus 0.88. So that's, oops, 0.88. Yeah, 0.12 mole fraction of solute. Okay. All right. So if that's actually, we may not need this one. We have a mass for water, 85 grams. So how many moles does that represent? Right? If we're working in mole fraction, we need to know how many moles of the solvent of water. Right? 85. Let's see. I don't want to overlap too much. I want to bring this one down here. So 85 grams of water is how many moles? Grams, moles, right? 18.02 grams per mole. Four point seven one seven moles of water. Okay. So if this is the mole fraction, 4.717 moles of water is 0.88. 0.88 equals 4.717. I'm probably doing this the hard way, aren't I? Moles of water per total. There we go. Why don't we do it this way? No, let me stick with that. 0.88. So the total moles is 4.717 divided by 0.88. .36. Total moles equals 5.36. So if this is the moles of water and that's the total, then the moles of the solute would be 5.36 minus 4.717, correct? I calculated the moles of water. Then I want to find out what's the total moles, right? Because the total moles would be the moles of the solute and the moles of the water added together. So then I subtract the moles of water from the total moles, and that gives me
6.432.
0.6?
6432.
Okay. So 53.8 divided by 0.6432. I get 83.6 grams per mole. That's it.
On here, you just, instead of doing the total, you just did 4.717 over 4.717. Down here. You just did this on top of this. And it just ended up equaling this instead of doing subtract
What did I put down here?
this. You put this on top of that.
Well, if I put that on top of that, that's one.
I know it didn't make sense.
Maybe there's another mistake. Which one is it?
2. You had 0.880 equals
Oh.
4.
4.717 plus the moles for solute.
Well, okay, yeah, that makes more sense.
Yeah,
Because I was looking at it and I was like,
no, that wouldn't
well,
work.
that's what you're getting, but I still don't understand.
Yeah, it just means there's more than one way to solve the problem. Yeah. This is the way I was thinking at the time. This is the way I'm thinking now. Okay. Number 4. Let's see, we have a 10.4 gram mixture of table sugar and table salt. When this mixture is dissolved in 150 grams of water, the freezing point is minus 2.24. Calculate the percent by mass of sugar in the original mixture. Didn't we have one of these in the lecture? I think we had one of these in the lecture, but I didn't have time to do it then. So we'll do this one now. Okay, so let's see, what do we have? 10.4 grams mixture. So the total mass equals 10.40, yeah, 0 grams. Mixture of what? Well, if we're going to have to determine the percent by mass of sugar and the total mass is this, then the mass of the sugar, if we let it be equal to X, then the mass of the sodium chloride, mass of sodium chloride is 10.40 minus X. That gives us the mass of each of our components. Dissolved in 150 grams of water. And the mass of the water equals 150 grams, or, and let's say we have, yeah, we do have that. This is 0.150 kilograms. Now, why did I do that? Because we're working in molality. It's per kilogram of solvent. Okay. The freezing point is found to be minus 2.24 degrees C. So the temperature is minus 2.24 degrees C, or the delta T absolute is all we need is 2.24 degrees C. Because the freezing point of water, pure water, is 0. So that's all we need. Okay, now we got everything on the board. We're looking for percent by mass. So eventually we're going to ratio this one to the total times 100. But first we got to find out what X is. Right, so let's go to the colligative property. This is freezing point depression. So the change in temperature, freezing point temperature, is equal to mass, right? Oh, this one will have a Van Hoff correction of 2, and this will have a Van Hoff correction of 1. Well, let's start with the overall. Mass times the freezing point constant for water times get mixed up. This is molality. I put that in here, didn't I? I didn't put it in here. Colligative property. That's crazy. I did put the factors. 1.86. KF for water is 1.86 degrees C kilogram per mole. This is 1.86 degrees C kilogram per mole. So molality takes care of that. Well, that's it. All we need now is the correction factor. Overall correction factor. So far, so good. Okay. All right. Here's the trick. We split this into 2. This is a linear combination. So this value here that we determined there is equal to I for sodium chloride times K times the molality of sodium chloride plus I for sugar times K times the molality of sugar. Okay. We'll split those apart. Okay. Now we can start filling in information. This is 2.24 degrees C equals, and we'll do this one. I for sodium chloride is going to be 2 times 1.86 degrees C kilograms per mole times the molality of sodium chloride. Molality is going to be 10.4 minus X divided by 0.15 kilograms. So it's 10.40 minus X divided by 0.150 kilograms. This is wait a minute. This is mass. All right. Get those confused with molality. So this is that's not going to work, is it? No. Wait a minute. Molality is moles. This is moles of sodium chloride. There we go. Okay, now I'm on track. And this is 1 for sugar, and with the same value here, 86. I'm not going to put the units in. And then this is moles of sugar per 0.15 kilograms. Now let's see if I have everything straight. Moles per kilogram, and this is kilograms of water. Yep. Okay. So how do we get moles of sodium chloride? moles of sodium chloride is this mass times, this would be in grams, so it'd be grams per mole. So we'd have the molar mass of sodium chloride. Did that before, right? 23 plus 35.45. $58.45. And this one is simply going to be sucrose. Does it tell us? No, it just gives us the formula. Okay, so carbon, let's see, 12 times 12.01 for the carbons, right? And then 22 times the hydrogens. And then 11 times the oxygens. Then we add those together. And 22, and then 16, 11. So I get 342.34. 342.34 grams per mole. 342.34 per mole. There we go. So this is going to give us moles. This equals moles of sugar. And this is moles of sodium chloride. So we would have to substitute those values in here. And then 0.150 kilograms. And this is sodium chloride. So it'd be this one. This would be 10.40 minus X divided by 58.45. Okay. And this one, I'm going to leave a 1 out. 1.86. And this one would be X divided by 342.34. X divided by 342.34 over 0.150. Okay. Now we have an equation in one unknown, X. Okay. So let's resolve this part in here. This denominator is in that denominator times this value, right? So 0.15 times 58.45 is 8.7675 divided into this value, but it's also divided into this one. So 1.86, divide that into that, and then times 2. And this is going to be equal to 0.4243 times 10.40 minus X, right? Because I brought this one into a divisor of that one, but I had to do this one first. This one times that one becomes a divisor of this term. That's where this came from. Then this stayed by itself on top. Okay. This one, 0.15 times 342, 42.34 times becomes a divisor of 1.86. And that's 0.03622 X. Because the only thing that was left here is X. And this became the multiplier of that because it's in the denominator. That becomes the divisor of this. And that's where this term came from. So now let's split these out. And this is still equal to 2.24. So 10.4 times that value. Let's see, split that. 10.40, excuse me, 10.40 times. So this times that is 4.4127 minus 0.4243 x, and this is still plus 0.03622 x. Okay, so let's get this one on this side. Yeah, might as well. Just change the sign. Right, it's going to be a negative when it comes over here. I'm going to do that again. 2.24, 4.4127. That's better. Minus 2.173 on that side. And then we add these two together. Let's see, this is a minus and that's a plus. So 0.4243, change that sign, and then 0.03622, add that together. This is a minus 2.597 x. So x is going to be this one divided into that one. And that's 0.837. So x is what? It's mass. This is grams. X is grams. And the question that we've been dancing around this whole time is, what's the percent by mass of sugar? Well, if this is the sugar mass and this is the total mass, then we just divide that by 10.40 times 100. And that gives us the sugar percent. And I get 8.05. Is that right? No. Now, where did I go wrong?
Question.
Okay. Well, let's go over here. I think this is it. Let's see if I did. All right. Total mass. Yep. Water, 150. Yep. 1.86, 2.24. Yes. That's right. Okay. Van Hoff corrections. We got that right. Molar masses, 5845. Yes. 342.34. Okay. That's good. Okay. X equals the mass of sucrose or sugar. And then 10.4 minus X is sodium chloride. Okay. Okay. So this is the delta T. This is the delta T of sodium chloride. And this is the delta T of sucrose or sugar. Okay. So we got that right. Then moles of sucrose over point. Yep, that's right. And that's right. Okay, so we're good down to here. And then, how did I do this one? Moles of sucrose. Okay. That's where I deviated. Yeah. I made it harder than it needed to be. So let's erase this. This. We're good to this point. Okay, now we're going to factor out things that we can from both sides. Okay. Moles of sodium chloride, moles of sugar. Probably ought to write write it like this. This is N of sodium chloride and N of sugar. Okay, we can factor out 1.86. So 2.24 divided by 1.86, we can bring that out of both of them over here. And we can also bring 0.15 out of there, out of both sides. Right, put this on that side. Now what do we have left? What we have left is 2 times the moles of sodium chloride plus moles of sugar. That's a lot simpler. So let's see what this one is. 2.24. Oops. And 0.15 and 1.86. So that's 0.6249 equals 2 times the moles of sodium chloride plus the moles of sugar. Okay. Oops. I calculated wrong, didn't I? Let me try that again. There. I must have put a decimal in the wrong place. Yeah, that's better. 0.1806. Okay. We can't solve that for one of the other of these because these are different values. So what we have to do is say, what is this equal to in terms of moles? Then we come back here. Right. 2 times, what's the moles of sodium chloride? Moles of sodium chloride is 10.4 minus X divided by 5845. Right. And the moles of sugar is simply X divided by 342.34. There we go. And that's equal to 0.1806. Okay. Okay, so the next step is I multiply this through here. That's 20.80 minus 2x. And this is over 58.45, and this is over 58.45. And this is x over 342.34. All right. We can get this term on that side. 20.8 divided by 58.45 is 0.3558. Bring that over here. It'd be a minus, then a 0.1806 plus. So this is minus 0.1753 equals what's left over here is I think I'm digging another hole. Oh, that's not even the right page. Messed up the pages. Oh, I see what I did. This is okay. Now this, we need a common denominator. So the common denominator How do you get a common denominator when you have two different denominators? You multiply this one times that one times that one. So now we're going to get, in the denominator, we're going to have 342.34 times 58.45. And if we multiply through denominators on this way, then this one becomes a multiplier of that one. Right? Oh, I didn't combine these first. I can combine these two, which is 20.80 minus 2x over 58.45. And then we can multiply yeah, now we got a common denominator. This can go away. I didn't leave myself enough room. Okay. Let's take this out. This, and let's just move it up. Move it up over here. So now we have minus 0.175 equals, and we're going to make a common denominator here, which means since this is 5842 and we multiply it by this, then this has to be multiplied by both of them. 342 times minus 2x. And actually, this is 20.80 minus 2x over 5845 plus x over 342.34. There we go. Now we have a common denominator. So 342.34 times 20.80 minus 2x. And then plus x, excuse me, 58.45 times x over, and this whole thing's over 342.34. So what we end up with is, if we do our calculations right, the x should be 5.60 grams of sucrose, and then we ratio that to 10.4 times 100, and that equals 53.8%. If I could do math, then it wouldn't take this long. So I'm probably into lab time already, huh? Oh, getting there. 5 minutes.
I think that was the last one.
Was it?
So,
Okay. Are there any questions so far, then?
I don't think so. I didn't really understand that one, if I'm honest.
Yeah. The trick to that one, well, you know that the colligative property is the freezing point depression, right? The trick to that one is splitting it out. Well, two tricks. Setting x equal to your unknown, right? We want to know what mass of sucrose there is. And that's the algebraic trick. And the other trick is a linear combination of freezing point depressions. One due to sodium chloride and one due to sucrose can be split out as additive. And from there on, it's just a massive headache of math.
Yeah, I think I'll just have to actually do the problem multiple times to figure out the math part.
Yeah.